Good afternoon, everyone. Welcome to the first talk of the string theory and the quantum gravity session. Our speaker, Marcos Mariño, is a professor of mathematical physics at the University of Geneva. He is an expert in quantum field theory and string theory, in particular on their interfaces with modern geometry and topology. Today, he will present resurgence, geometry, and physics towards a unified approach. Please join me in welcoming Professor Mariño.
Okay, thanks a lot. First of all, I would like to thank the organizers of this amazing Congress and also Professor Yao in particular for this invitation. This is really an amazing place, an amazing hotel. Everything is amazing. So I will give a talk, which is going to be a review talk. So it's going to be like light, okay? And as you can see, in my title, there is geometry and physics. So let me try to motivate, oops, here maybe. Okay, so there is geometry and physics in the title. And actually what happens is that sometimes concepts that were introduced in physics actually turn out to be very useful and have a second life in a more geometric context. And a very good example is supersymmetry. Supersymmetry was introduced in physics for physical reasons, but then it turned out to provide a physical model of cohomology and led to topological field theories, to VPS invariance, to many things. So supersymmetry was born in physics, but eventually had a deep impact in geometry. So in this talk, I will argue that some ideas developed in physics to understand the information hidden in the divergent series that appear naturally in physics lead to novel perspectives in geometry and topology. So these ideas in physics I will review first, and sometimes they are known under the name of the theory of resurgence. And what I will do now is to give some sort of historical overview of resurgence at a very introductory level. And then I will try to make the contact with geometry and physics, okay? Okay, very good. So a good point to start with resurgence is an old story, which goes back to Dyson. So the story of resurgence always starts with perturbative series. Can you actually make a full view of because there is all these things on the side. I don't know, maybe I press a button without, okay, sorry, thanks. So perturbative series have played always a very important role, but in particular in quantum field theory, they are really fundamental and they become essential truth. So the first question you can ask is, okay, all these perturbative series that we compute in quantum field theory, what is their nature? Are they convergent? Are they divergent? And Dyson realized as far back as 1952 that the perturbative series unlisted in QED must be divergent. So he pointed out if you compute an observable in QED as a power series in the string coupling constant, this series is going to be divergent, and more precisely, the coefficients will grow factorially. So what was the argument that Dyson made? So the argument of Dyson is very qualitative and heuristic. So the argument is pretty much the following. So imagine I have a series which is convergent when you expand around the origin. So this must mean that it must describe the physics of both positive and negative coupling. Okay, the same function will describe the physics when the coupling is slightly small and positive and slightly small and negative. But this is impossible, said Dyson, because the physics of QED is completely different if the coupling is positive than from the coupling is negative. The coupling is negative, the vacuum is unstable, and you have a totally different physics. So the heuristic argument of Dyson is you cannot have the same function describing both these physics of positive coupling and the physics of negative coupling. So you cannot expect this physics to be described by the same convergent series. So this is an heuristic qualitative argument, but the argument became quantitative with a very beautiful work that Bender and Wu did in the early 90s, 70s. So what Bender and Wu say is, okay, quantum field theory is complicated. Let's try to look at quantum mechanics, which is much simpler, and see how this argument works. Okay? So a very simple situation that you are exposed to this situation when you are an undergrad in quantum mechanics is to study the perturbative series in a standard Schrödinger perturbation theory. So you can, for example, take the harmonic oscillator with a quartic perturbation and try to compute, say, the ground state energy of this system as a function of the coupling, as a series coupling. And this is, I said, something that you might have been done as an undergrad. So this is the quartic potential that you have. And actually, this series, you can check that this is also factorially divergent. If you compute enough terms, you will see very clearly that the factorial growth of the coefficients turns on relatively quickly. Now, Dyson's argument suggests that if you want to understand what happens in this theory, you have to look at the theory when the coupling becomes negative. Remember, Dyson said if the coupling becomes negative, the physics is going to be different. And this is what makes this series divergent. So looking at the theory with negative coupling could explain the divergence of this series. Now, what happens if you actually change the sign of the coupling? Well, you will have still a harmonic oscillator around the origin, and at some point the quartic coupling with negative sign will turn on, and you will have an inverse situation like this. And of course, the physics of this system is very different, right? This is an unstable potential, but in particular, you have something new here. You have an instanton now tunneling between these two vacua, the two critical points of this potential. And actually, what Bender and Bush show is that this tunneling amplitude gives a precise quantitative prediction for the behavior of the perturbative series, for the divergent behavior of the perturbative series. So remember that tunneling amplitude in quantum mechanics is exponentially small in the coupling constant. You have something like this. This goes essentially as e to the minus a over g, where a is a numerical constant you can compute. And what Bender and Bush showed is that the factorial divergence of the coefficients of this perturbative series that I show you here, so the coefficients appearing here, the coefficients an appearing here, are going to diverge like n factorial times this instanton action a to the minus n. So this was the argument of Bender and Boom. And at this point, I need a more powerful mathematical construction to understand this type of relationship. And this is going to be the concept of a resurgence structure. So this is where the math comes in. And I will have to use now some math in order to make progress with this talk. Okay, so what is the resurgence structure? This is actually a quite simple thing. Now, imagine that you have a formal power series, phi of z, in which z, you can think about z as the coupling, in which the coefficients grow factorial. Now, there is a very simple way to actually get rid of the factorial divergence by doing what is called a Borel transform. A Borel transform is a map between this series, this formal series, and another series that I'm going to call phi hat of zeta. Zeta is a new variable in which you just divide an by n factorial. Now, when you divide an by n factorial, you cut the factorial growth. And remember that the typical situation is that the coefficients will grow like n factorial times a factor a to the minus n. So once you divide by n factorial, the series will grow just exponentially and will have a finite radius of convergence. That's the key thing of the Borel transform. It takes you from the world of factorially divergent series to the world of analytic functions at the origin. And this is a big thing because, working with holomorphic functions at the origin is a great thing to do because you can use all the techniques of complex analysis. Now, so this Borel transform is analytic at the origin, but of course, as you start moving away from the origin, you can expect that this function will have all kinds of singularities. You can have poles, branch cuts, and so on. So you represent this function in what I call the Borel plane, which is the plane for this other variable that I introduced here. So this is called the Borel variable. This function is going to have a finite radius of convergence around the origin, but as you move away, you will find singularities. And the location of the singularities I will denote it by zeta omega. So omega is an index to denote the singularities. And essentially, the main point of this talk is that this Borel plane, the structure of the singularities of this Borel transform, has a lot of information about the non-perturbative structure of the field. Okay? So what happens when you have a singularity? Well, singularities can have of many different types. You can have poles, you can have logarithm branch cuts, you can have power branch cuts. So let's assume that, oops, that's something that happens from time to time, that some of the equations disappear from this. This has happened to me before. Can you actually try to solve this? Because it's going to be very hard to give a talk without equations. There are not that many equations in my talk, but there are a few of them I wanted to be shown. So you probably need another PDF reader. Sorry? Really? No. Well, I have it on my own computer, yes. Yes, yes. I think I brought my own computer. Sorry about this. It's funny, this has happened to me many times. And this is, yeah, no, I can use my own computer, don't worry. It's a pity because, this breaks the thread that I was. Yes. Okay. Just 1 second. Okay. Second. Yes. Okay. Uh, uh, okay. Can you see this? You can see this guy there. You know him. Yeah, this is later. Okay, good. Here I am. You see, this is the question that I was missing. Yeah. So, it's funny because it looks like one of these hieroglyphs, right, from Egypt. Some things have disappeared, so you have to code. So let's assume that. So the main point here, as I was saying, is that you will have singularities in the Borel transform, and then when you expand around a singularity, you will find new information. Okay, and the main point here is that when you expand this Borel transform around the other singularities, you will find new formal power series. And let me give you an example of this. The simple example you can have is when you have a logarithmic branch cut. So you have a logarithmic branch cut. This means that when you span around the singularity, which is xi omega, you will find a logarithm multiplied by a holomorphic function. And this holomorphic function will have also a coefficient in front. So that's this split in between this function and the Stokes constants, this constant here, which is called Stokes constant, depends on a choice of normalization of phi omega. So I will in this talk use always good normalization so that the Stokes constant will have interesting meaning, as you will see later. Now, the interesting thing here is that you have here an analytic function, but this analytic function, you can do an inverse Borel transform, so you can expand it locally around the singularity and multiply every coefficient by n factorial, and then you will get another formal power series. So in a sense, what is going on is that when this Borel transform, you expand it around the origin, you have the information of your original perturbative series. But when you go to other singularities, you have popping out of these singularities, you will have new formal power series. And what's the meaning of these new formal power series? Well, the idea is that this new formal power series will give you information of the non-perturbative sectors with it. So let me summarize. So the local analysis of the Borel transform singularities will give you a new power series, which is also in principle a divergent series, plus Stokes constants. And the collection of all these power series of the Stokes constants from all the singularities of the Borel transform is what we call the resurging structure of the perturbative series. And under some mild assumptions, this is a well-defined problem with a unique answer. I give you an infinite perturbative series. You do this Borel transform. You look at what happens in the plane of singularities. You have to extract all this information, and this is a well-defined problem in complex analysis. Okay? And this you can do with any theory you want. What do you mean the dependence on what? It's a number. It's a complex number in principle. Yeah, for each singularity and for given a normalization, this is very important. You have to give me a good normalization of this power series. You will have different Stokes constants, which are complex numbers in general. Okay. What do you mean is a branch point? Yes. Well, yeah, but this is for me, anything which is non-holomorphic is a singularity. So you have like say a square root branch cut. This is a singularity for me. So singularity in the sense of complex analysis. You don't have to go to infinity. As long as it's singular, it's okay. Yes?
Yeah. Power series truncate.
Yes. Now the power series truncate, then this is not a factorial divergent series, right? So yes, but that's different. That's not what I'm talking about. I'm talking about the resurging structure associated to a factorial divergent series. Okay, that's another issue that we can discuss later on what happens in those cases. Okay, now as I said, one of the reasons we're interested in this resurging structure is because it gives us a window into non-perturbative physics. And indeed, with the information which is encoded in each Borel singularity, you can construct what is called a non-perturbative object or Trans series. So a Trans series is something which goes, as the name indicates, goes beyond a series. So remember that singularities give you a formal power series attached to them. They give you a Stokes constants, but it's the natural thing to do with this series is to actually multiply by an exponential, which is minus the location of the singularity divided by z. And this object is no longer a formal power series because it has a small exponential, and this is what it calls a Trans series. So there are reasons why this is the natural non-perturbative object to obtain from a singularity. I won't have time to explain it in detail, but believe me that this is actually a natural construction when you do this Borel transform. If you are familiar with this, you do, for example, you calculate the discontinuities of Borel resummations. This is the natural object that is attached to a singularity. Okay? But here, just let's follow just the pattern that you do the Borel transform, you look at the singularities, to each singularity, you calculate this Stokes constant, this series, and then you construct this non-perturbative family. Okay? Very good. Now, remember that one of the ways in which people discover this is by looking at the large order behavior of the perturbative series. And it turns out that the large order behavior of the original perturbative series is quantitatively determined by the Trans series, which is associated to the closest singularity. So imagine that you do this analysis, and the closest singularity you find to the origin is this one at the location psi omega. So associated to this singularity, there will be a Trans series, which typically has this form. You have this exponential here, the Stokes constants, and then you have formal power series. And in general, you might have a factor c to the minus b, where b is not necessarily an integer. And then what is very beautiful in the sense is that the divergence of the original series, the factorial divergence of the original series, is quantitatively determined by all these coefficients here. You see, the Stokes constant becomes an overall constant. The b here appears as a correction to the factorial behavior. The location of the exponential gives you the factorial growth, which is subleading to the exponential growth, which is subleading to the factorial growth. And all the terms that appear here give you 1/n corrections to the asymptotics. So essentially, you can read this equation in two ways. If you give me a perturbative series and you really know how it diverges with all these precisions, you can reconstruct this object, or the other way around. If you know this object, you can determine the factorial divergence of the perturbative series with very great precision. And actually, this was fundamental for the work of Bender and Wu. They did really experimental mathematics. They generated 80 terms. They're talking about the early 70s. They generated 80 terms of the perturbative series with one of these mythical computers of the period. And they were able to actually compute these asymptotics numerically, and then they fitted it to the expected instant on amplitude. So it was quite impressive what they did. So you can actually get this by using essentially a sort of Darboux theorem. Okay, the Darboux theorem tells you that when you have an analytic function, the growth of the so this is maybe because my computer is not connected. Next problem. Okay, and then the Darboux theorem tells you that the behavior, the growth of the coefficients is determined by the next singularity for holomorphic functions, and then you multiply by n factorial and you get this result. Okay, it's essentially a consequence of Darboux theorem. Okay, now in the Bender-Wu example of the quartic oscillator, the leading singularity that you find is on the negative real axis and corresponds to an instant on amplitude at negative coupling. Remember that in the original problem, the coupling is positive, but in order to see how it diverges, you have to go to negative coupling. So you have an amplitude that grows actually like 1/3g because the amplitude is here. So the singularity is here at the negative axis. Actually, with correct normalizations, this is -1/3. Okay? So this is, in a sense, a very simple example of a resurgent structure appearing in quantum mechanics. You take the series of the quartic oscillator that you compute as an undergraduate quantum mechanics student, you look how it diverges, and you will find this singularity here with this associated amplitude. Okay, it's a simple example. Is actually the action of the coefficient of the exponential. So I call it A, exactly. It's a normalization in which you take the h bar equal to 1, m equal to 1, maybe or 1/2. Okay. That's a normalization that I use here. Now, yes. Yes, absolutely. Absolutely. No, I don't think here, I think, this is really only thing that you really need here mathematically is that this series essentially is such that when you divide by n factorial, this has a finite radius of convergence, and then you can analytically continue. This is the only thing you really need. So you can do this level by level, for example. So this is what I did here. This is for the ground state energy. But yeah, in principle, there are no mathematical subtleties with that. Okay. Now, of course, this is quantum mechanics, but the question is what happens when you take a realistic quantum field theory. Now, for a long time, actually for essentially the whole 70s, people assumed that the resurgent structure will be due to instantons, as in quantum mechanics. And it was a major surprise. Edouard Bressan told me recently in Paris that, it was really a shock for them, these people who were working on quantum field theory in the 70s. It was a shock that most Borel singularities in the Borel plane of quantum field theories respond to instanton amplitudes, but to more mysterious objects, which are called renormal. Okay? So this is actually a complicated story, but here we have very clever people, Parisi and Toff, who were the first ones to actually start looking at renormalons seriously. And they actually make a very interesting conjecture in the case of asymptotically free series. So in the asymptotically free series at infinite volume, they claim that they will find singularities in the Borel plane of the perturbative series, and these singularities will occur generically at integer multiples of 1/2 times beta 0, where beta 0 is the first coefficient of the beta function of this asymptotically free series. So essentially, there are all these singularities which are not of origin, and there was a lot of discussion about what's the meaning of this. But one thing you can see very quickly, just a very kind of back of the envelope argument, is that you remember that every time you have a singularity, you will have an exponentially small correction. So an exponentially small correction, which goes like d/2 beta 0 g mu, is actually proportional to the dynamical scale of the theory divided by mu, where mu is the mu of the running coupling constant, to the power d. So these are sometimes called power corrections, and they do not have a semi-classical description. They really indicate that you cannot really understand path integrals in these gauge theories, in these asymptotically free theories, in terms of semi-classical saddles only. So there will be, lambda is the dynamically generated scale of the asymptotically free theory. Okay? No, d can be in principle any integer. Okay? It's an integer. Well, there can be, now this is the generic position. Now, depending on the theory, not all d will be actually covered. This was the generic conjecture of Parisi and Toff. Now, so this is very interesting because these are exponentially small corrections to perturbative series which do not really have a clear semi-classical origin. And the people realized, in particular Parisi realized, that these non-perturbative amplitudes can be obtained in some case by using something which is very close to semi-classics but not completely semi-classical, which is the operator product expansion. But if you want to do this, you have to assume that the operators in the operator product expansion have non-perturbative backing expectation values. And this is exactly what Shifman, Meister, and Sakharov postulated in the late 70s, early 80s. Yes. Well, no, the beta function is already accounted here. This is different. This is the dimension, right, of the operator that appears in the OPE. Yeah, in some supersymmetric theories, yeah, but I'm not really talking about supersymmetric theories. Supersymmetric theories, from the point of view of resurgence, are very special. No, I mean, people have studied these theories in supersymmetric theories, but it's maybe very non-generic supersymmetry from the point of view of this study. Okay? So you can actually do, of course, this in supersymmetry, but of course, you will have all kinds of rules, that selection rules that tell you that maybe many operators will not appear and so on. But I'm talking here about generic expectations. And I think there is a lesson here, as I said, there is a lesson to be taken here. And I say this because I realize that most of string theories are very fond of saddle points, that actually, even in simple theories, even in asymptotically free theories, in the ultraviolet, I mean, in the ultraviolet limit, I'm not talking about the infrared. Infrared is very complicated. Even in the ultraviolet limit, the corrections to the perturbative series are not given by semi-classical saddles. That's an important lesson. Now, the resurgent structures that are associated to these renormalons is the name that we give to these singularities, are often used in QCD to model non-perturbative effects. So let me just give you an example, which is very well known for QCD people, which is the Adler function in QCD. So you take the quark current here, psi and psi bar are quarks, and then you calculate this 2-point function. This is called the Adler function, and then this has a perturbative series that you can calculate. And then you look at the Borel plane, and then you will see that there are two singularities which are close to the origin. There is one on the negative axis, which is a renormalon. It's sometimes called the ultraviolet renormalon. This is not that it's not that important. The singularities which are more important for quantum field theories are the ones in the positive axis. And the first singularity you find is a famous renormalon, which is due to a non-perturbative gluon condensate. So this singularity is telling you about a non-perturbative effect in QCD, which is the fact that the gluon operator, trace of F mu, has a non-trivial expectation value. And in a sense, sorry? Yeah. No, this is the Borel plane. But yeah, you're assuming that you are expanding in G of Q, the coupling constant at the scale set by Q. Okay? So after removing factors of Q, you can write this as a function of the running coupling constant at the scale set by Q. Okay? So this is really a singularity which is not due to a saddle. Now, at the same time that physicists were exploring the Borel plane, Jean Ecalle, a French mathematician, developed a very original mathematical theory of resurging structures. And Ecalle was interested on a different source of perturbative series. What Ecalle was interested in is the series that appear when you solve non-linear ordinary differential equations. I mean, you have actually solved many times ordinary differential equations around irregular singular points in which the perturbative series that you obtain is also a divergent series. And this is the kind of series that Ecalle was interested. So typical example is this, rank 1 ODE, which you take a function, the f, which satisfies this equation, and now you're going to expand around z equal to infinity. This is the typical convention for ODEs, but again, you find a divergent series in 1 over Zn. And actually, if you look, you can also look at the Borel plane for these solutions, and you will find singularities of this type. Okay, so this is again a universal phenomenon. I give you a perturbative series. You can always look at the Borel plane, and in this case, you will find this type of singularities. And Ecalle was very interested in calculating, for example, the Stokes constants associated to these singularities. And he developed an amazing, beautiful analytic framework in which he was able to express the Stokes constants explicitly in terms of the coefficients that appear in this equation. So he developed a very beautiful machinery. And this is a beautiful machinery because it relates with perturbative and non-perturbative data. So the coefficients that appear here is essentially the basic building blocks for constructing your perturbative series. And then he was able to write analytic formula for the Stokes constants in terms of this coefficient. So this was a very beautiful achievement. And this was very influential in the development of resurgence. Now, since this is a string theory section, the ideas of resurgence have been also used in string theory, because in closed string theory, amplitudes are expected to grow factorially with the genus as 2G factorial. So this was an observation that was made famous by Schenker in the early days and was triggered in particular by the developments in non-critical string theory, where this growth, you can see it very explicitly by solving, for example, Pan-Level 1, which gives you the specific heat for the minimal string coupled to gravity. And actually, it's very important to notice that this was one of the motivations of Polchinski to introduce the brains. And remember, in 1994, Matthias and I were in Les Souches, where Polchinski was giving talks on this, and Polchinski had just discovered the brains, not yet in connection to string dualities, but his main motivation was to understand this 2G factorial growth. And he noticed that these D-branes, these Dirichlet boundary conditions that he has introduced in string theory, were useful to actually explain this. This is before the superstring revolution. And indeed, there is evidence that if you take closed string amplitudes, a perturbative series in the genus, and you look at this resurging structure, you look at the Borel singularities, these are going to involve D-brane instantons. And in non-critical string theory, this is very well tested. And as you will see in a moment, this is also the case in topological string theory. D-branes are the natural objects associated to the Borel singularities of the perturbative genus expansion. Now, so we have seen the idea of resurging structures is a very beautiful unified analytic framework to understand non-perturbative phenomena. You give me your favorite perturbative series in quantum mechanics, in quantum field theory, in string theory, and there is this universal approach to understanding the non-perturbative structures. You can also do it in dynamical systems, as Jean and Ecalle did, and you get information about these non-perturbative sectors of the theory by looking at the Borel plane. But this is, in general, a very difficult problem. I mean, in generic quantum field theory, we have some indications, we have this conjecture of Parisian Toth, but we don't really are able to calculate the resurging structure in detail. And one thing that you could say, okay, what happens if we go to a simpler type of theories where you have at the same time some sort of topological constraint, and at the same time you have a non-trivial perturbative series that you can use. And the idea is precisely what happens when you apply this framework to topological field and string theories. Now, when you calculate a perturbative series in a topological theory, the coefficients of the perturbative series are perturbative topological invariants. For example, in the case of Chern-Simons theory, this has been known for a long time. There is this famous LMO invariant, for example, which is a way of extracting perturbative topological invariants from Chern-Simons theory. So you will get perturbative information which is topological in origin. Now, since everything is topological in a topological field theory, you expect also that the information you get from the Borel plane is also going to be topological. Okay? Yes? Oh, no, I'm not saying that there is a connection. The framework is the same. This is a very generic framework. But the question is that in each theory, you will have a different source of non-perturbative phenomena. In quantum mechanics, these are instantons. In string theory, these are D-branes. And in quantum field theory, these are Renormalons. So you see, they all come, you have the same framework, but the physics of the singularities is different in each theory. I'm not saying that there is a connection. Actually, it's a very interesting question because in a sense, you can say that D-branes are Renormalon type. Because Renormalons come when you do an integration over the Feynman diagrams, and the integration grows very fast. And it's not a growth, the factorial growth is not due to the number of diagrams, but to the moduli space of the Feynman integral. So it looks like in string theory, this is actually what happens. You have essentially one diagram, but it depends on the way you count. You have essentially one diagram per genus, and it's the integration over the moduli space of Riemann surface which gives you this factorial growth, because the volume of Riemann surface grows like 2G factorial. So it looks like, in a sense, in string theory, you could say that these are of Renormalon origin, but it's a little bit, has not been really studied much in detail. Okay. Now, it turns out that in these topological theories, you can't really get much closer to an analytic determination of the resurging structures. And surprisingly, for me, the most surprising outcome of all this line of development is that you will find Stokes constants, because this is a universal feature of this approach. And the Stokes constants actually in these topological theories are integer topological invariants. So you start with a theory in which you have perturbative topological invariants, you calculate the Stokes constants, and you get integer numbers, which are actually related to an appropriate counting of BPS states in a closely related supersymmetric theory. So in a sense, you could have discovered BPS invariants by doing the resurgence in the perturbative series that appear in these theories. And I think mathematically this leads to a novel perspective on BPS invariants and also what they are called the wall-crossing structures, in the sense that they are encoded through this resurgence in the perturbative simpler invariants that you obtain directly from perturbation theory. So no. Well, why minimum? What did mean minimum?
So,
Yes. Oh, I see. Yeah. Well, I don't really have a very clear kind of microscopic picture of what it happens. At this point, I think we are more on the level of discovering this connection, right? But maybe we can. Let me just explain you the examples, and maybe this will be clearer. Now, I will actually discuss two examples. One is complex Chern-Simons theory on hyperbolic knots, where there are perturbative invariants associated to this, and we will see that corresponding Stokes invariants are three-dimensional indices. And the other case are topological strings on Calabi-Yau threefolds, where the perturbative invariants are essentially Gromov-Witten invariants, and it turns out that the Stokes constants will be Donaldson-Thomas invariants. A perturbative invariant means that if you take topological field theory and you calculate a perturbative series, each coefficient in the perturbative series will be a topological invariant of the theory of the manifold that you are considering. For example, in the case of Chern-Simons theory, this is what people call sometimes Vasiliev invariants, which are related to the perturbative series of Chern-Simons theory. In the case of topological strings, these are Gromov-Witten invariants. This is what I mean by perturbative invariants. They are invariants that appear when you do a perturbative expansion in the underlying theory. Okay? Now, let me give you an example in Chern-Simons theory. Let's take your favorite hyperbolic knot, and there is a very beautiful perturbative invariant of hyperbolic knots, and we have the privilege of having the inventor of this invariant here in the room. Where is Rinat? Rinat. So Rinat introduced an invariant, and there is you can think about this as an all-order perturbative invariant. And this invariant was introduced in mathematics by Rinat, but it describes the expansion of SL2C Chern-Simons theory around a particular connection in the moduli space of connection, which is what we call the geometric connection. The geometric connection, remember that complex Chern-Simons is related to 3D gravity. So there is a connection in the manifold which corresponds to the hyperbolic complete metric, and this is what I call the geometric connection. So this is something that it's a machine compute very explicitly. So you take, for example, the figure A knot, which is our favorite knot, hyperbolic knot. You can actually compute this power series. Tau here is you want the coupling constant of complex Chern-Simons theory, and you can compute this, and you see all these crazy numbers. And now exercise, take this series, which is very well defined, and try to find its resurging structure. It's a factorial divergent series. So where are the singularities in the Borel plane? What happens? What do you find in these singularities? And it turns out that this is one of the few examples in which you have a complete description of the resurging structure. And this was work that I did with Jay Wu, who is here in China, and Stavros Garoufalidis, who is also in China. And we actually got a very precise description for the Borel plane. So we found all the singularities in the Borel plane, and we actually computed with a particular normalization of this trans-series. We computed the Stokes constant, and they turned out to be integers. Okay. Now, there are two types of singularities here. There are also singularities in the lower half of the plane, but I didn't show them here in this transparency. So these singularities, remember that in each singularity you have a power series and a Stokes constant. The power series that appear here are the same ones that appear here. So this series replicates itself on the imaginary axis. Okay. The fact that you have this sort of lattice structure is due to the multivalueness of the Chern-Simons action. So this means that the instantons, if you want, come with period 2 pi or 4 pi squared, depending on normalization. And here we have another family of singularities, and the transseries associated to each of them is what is called the conjugate connection, which is actually the perturbative series that you would obtain by expanding around the complex conjugate of the geometric connection. So we really have a very clear description of this. And the Stokes constants with the natural normalization of the series are all integers. And when you have an integer, you have to suspect that there is some sort of enumerative meaning to this. And indeed, it turns out that these numbers that appear here are actually an index. This is the Dimopte book of Gayotto book of index, which actually counts BPS state in a very natural supersymmetric theory, which is the one that appears in the 3D duality. So these are this counts BPS states in the 3D superconformal field theory dual to this hyperbolic knot. And this relationship was conjectured by us to be true for any hyperbolic knot. Any hyperbolic knot, the all orders Kazhaev invariant, the responding structure will have a specific set of Stokes constants which correspond exactly to this index. And recently, a group of people, Andersen, Kontsevich, Fantini, and Wheeler, have announced a proof of this conjecture. So they have a very beautiful proof in which they actually compute this Stokes doing by looking at a really different saddle points of this complex Chern-Simons theory and so on. There's a very beautiful picture. And you can confirm that these Stokes constants are actually indices. Yes? Yes. In a sense, you're really counting. There is this Witten picture of complex Chern-Simons theory in which you are essentially counting flows from one critical point to the other. You see, so you can think about this as the trivial geometric connection. This is another connection, which is the geometric connection plus some multi-covering, and then there will be a flow, and if you count this sort of, you do some sort of Morse theory counting, you will get these numbers in this way. Okay. Yes, there is an argument which was never published, unfortunately, by Greg Moore and Gayotto. After we wrote this paper, they found some sort of argument, using this sort of this 6D theory in which they could relate both things in sort of a priori way. But unfortunately, they never published this. I have to say that the proof, the mathematical proof, is less is more concrete, but they don't really use this Witten picture. They use more like a picture of really looking at the complex Chern-Simons integral and counting this flow in a sort of simplified model. You can think about this as it's like they had a localized version of the path integral of Chern-Simons, and they do the argument for a finite dimensional integral. So it's a little bit different. But there is a very interesting physics here. Yes. Of these guys, well, I don't really know. Really look at that. Yes, there is a trisomy one here, right? So there is a sense. Yeah. Now there is of course another tower here, and this tower has also can be related to an index by doing a slightly more complicated version. But this is kind of very clean because this is directly on the nose, the index that they calculate. Okay. Now I'm going to go now my second example, which is a little bit more complicated, and this is the case of topological strings. Now so let M to be a Calabi-Yau threefold, and at each genus G, you can actually calculate a perturbative topological amplitude, which is the topological string differential genus G, and this is a function of the model of the Calabi-Yau X. Okay, so this is something that X, if you use what is called the type A picture, X are complexified Keller parameters, and this is slightly more complicated than the example we had before, because here I use an example in which the perturbative series was purely numerical. Okay, but here I have a series which is slightly more complicated in the sense that the coefficients themselves depend on moduli. Okay? And this is the next stage of complexity. This is sometimes people call this parametric resurgence. Now, these functions f of x, they are very famous because they encode the Gromov-Witten invariance of this Calabi-Yau manifold at genus G. So if you expand this function in the limit in which x is large, which people call the large radius limit, then this will have an expansion in which the coefficients are perturbative topological invariants, which are called Gromov-Witten invariants. Now, in string theory, you don't want to look at the expansion of Fg as fixed G, because this is actually a convergent series. There is nothing to do with resurgence. But what you want to do is to really consider the expansion in the string coupling constant. So you form a formal power series in which you put together all the genera from genus 0 to infinity, you multiply by the string coupling constant, and as Schenker pointed out long ago, the series is going to grow 2G factorially. I have to say that very recently, there was a mathematical proof that at least in some case, on the local Calabi-Yau case, you can actually prove that this actually is true. Okay, so it was proved based on topological recursion. It's known that topological recursion computes these functions in toric Calabi-Yaus. So there is now a proof that for a wide class of families, you really have this growth. Of course, this was observed empirically, but now there is a proof that you have this 2G factorial growth. 15 minutes. Oh, more than 90. Yes, sorry. Absolutely. This function satisfies the holomorphic anomaly equation. Absolutely, but it's not complete. You need boundary conditions for this recursion. So you can only fix it in some cases, not in general. That's a good question. It has not been done, but I will mention this in the next transparency. Okay. In any case, this is again, you have this function, you have your universal machine, you compute now the Borel transform, and you try to look at the singularities. And now it's very important that everything depends on X. So now as you move in the Keller moduli space of the Calabi-Yau, singularities will start moving, okay? And that's another important aspect of the story. So everything now is X dependent. So what are the singularities? Now, I'm going just to state the conjecture, okay? So the Borel singularities for the series are conjecturally of the form L times A, where L is a non-zero integer. So the singularities come into what you would call a non-perturbative multi-covering structure. In geometry, people who work on Calabi-Yau know that every time you see a geometric object, the multiples of this object also appear. This is a well-known phenomenon in Gromov-Witten theory, and here it also happens. So if you have a singularity at A, you will have a singularity at 2A, 3A, and so on, and also in minus A, minus 2A, and so on. Okay. Now, what is A? A is the location of this singularity, and it turns out that A is the central charge of a BPSD brane, the Calabi-Yau. So you can actually label, again, in this A model, the charges of the branes are given by elements in the even cohomology of the Calabi-Yau. So you can think about DI as 0 and 2 homology and CI as 4 and 6 homology. And then A is typically given by a linear combination where X are the moduli of the Calabi-Yau and Fi are the dual moduli. So this is the derivative of F0 with respect to Xi. So this is the typical central charge of a D-brane with these charges. So that's also very beautiful because it's saying that the D-branes, the spectrum of stable D-branes on the Calabi-Yau can be read conjecturally from the Borel singularities of this theory. Okay? And now the question is, what are going to be the Stokes constants? We saw in complex Chern-Simons theory, these Stokes constants are BPS indices. So maybe here is also the case. And the conjecture is actually that the Stokes constants associated to these singularities are actually the Donaldson-Thomas invariants or the BPS invariants counting states for this D-brane. Okay? And so this actually was very surprising to us. There is a lot of information that seems to support this fact. And the surprise is that Donaldson-Thomas invariants can be in principle computed from the behavior of the topological string free energies large genus. Okay. Now remember that the Donaldson-Thomas invariants have this what is called this this wall crossing behavior. So as you move, these singularities will disappear. So BPS states will disappear, other will appear, and actually this is actually very interesting because you see there was this story with the OSD conjecture in which they were trying to connect Donaldson-Thomas with topological string free energies, but there was this puzzle of the topological string free energies are really functions, so they don't really have any sort of wall crossing, right? how are you going to explain the wall crossing if you start with FGs? Well, it's a known fact in parametric resurgence that even if your functions are continuous, the singularities will have wall crossing in general. And this was already discovered by Ecalle and Voros in the context of quantum mechanics. You just plot if you take a potential in quantum mechanics and you plot the Borel singularities associated to the WKB series, the singularities will actually go through wall crossing behavior. So this was known already in quantum mechanics. So this is a beautiful way of actually making both things compatible. The functions themselves do not have wall crossing, but the singularities do. And this is something that really Resurgence is very natural, and it actually makes possible that you can extract the Donaldson-Thomas invariance from this perturbative invariance. Okay? No, this is the relation is really purely perturbative. So this is a non-perturbative relation. You really have to go to large order behavior. It's a different type of relation. Well, in principle, not. Yes. 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 You see where the singularities are, in the Borel plane, and then you move in moduli space, and for each value of x, you will have different sets of singularities, and sometimes the change of these singularities is discontinuous. You can have, for example, singularities appearing from nowhere, and this you can really check. For example, in cyber-Witten theory, we know that this is the simplest example of wall crossing. You can calculate these FGs for cyber-Witten theory. This is this geometric engineering and so on, and you really see this. You really see how the singularities go. You go from the strong coupling spectrum to the weak coupling spectrum, and you see it on the nose by looking at the Borel plane. So the Borel plane is really telling you about this, and it's telling you it really has wall crossing behavior inside it, right? And this is because of this parametric dependence. The parametric dependence, as I said, is continuous on the perturbative series, but this is discontinuous in the Borel plane. It's a very beautiful aspect of Resurgence, which actually makes these statements possible. Okay, so let me conclude. So I hope I convince you that this mathematical concept of Resurgence structure gives you really a unified framework to understand many non-perturbative phenomena in physics. It's actually a very generic construction, right? And then you apply it in different places, and then from the perturbative series, you get instantons in quantum mechanics, Renormalons in quantum field theory, Divergent in string theory. And I have to say that obtaining explicit results on these structures is very difficult. But as I try to convince you in topological theories, you can make a lot of progress because you have much more millage. I have to say, for example, that something that I didn't mention because I didn't want to talk about everything in my talk. But for example, if you consider quantum field theories which are integrable, then you get a much better understanding of Renormalons, for example, that you can get in QCD. And we did a lot of work in integrable asymptotically free theories like the Gross-Neve model, the non-linear sigma model. And then you really see the Renormalons in a much better way than in QCD. In QCD, it's hard to make statements unless you do some sort of large number of flavor approximation or something. So understanding these structures when you have a more restrictive type of theories is easier. And then, what was surprising in a sense is that you get a new viewpoint on BPS invariance. You don't think about BPS invariance as some fundamental objects. You think about BPS invariance as those constants associated to a perturbative series. And this gives you a new perspective, which is maybe not as powerful in terms of calculations of this BPS invariance, but makes a very beautiful connection. It's a very beautiful realization of the perturbative non-perturbative connection at the level of geometric invariance. Now, let me also make a comment that in this development we made a change of emphasis, because when people are computing these Borel singularities and the series attached to them, if you are a physicist, what you want to do is to get new non-perturbative sectors that then you can add in some way to your perturbative series. And by using resummation techniques, you can actually reconstruct an observable. So people here, if you notice, I have not mentioned resummations at all. Of course, if you really want to calculate observables, you want to do resummations. But if you're really interested in extracting Stokes constants, you don't have to do resummations. Stokes constants are intrinsic properties of the singularities of the Fourier transform. So you don't have to do any resummation. They are really very solid objects. And then, since you want to do these applications to geometry, the Stokes constants are intrinsically associated to the perturbative series. And then, the emphasis is put more on the determination of the structure of the singularities than in doing resummation things, right? Now, there has been a lot of recent progress on this resurgent analytic theory, but I have to say that in many senses, there are still many things to do. And for example, one thing that I dream to do, remember I mentioned that Ecalle found this very beautiful analytic formula for Stokes constants, and it would be very beautiful to have some generalization of this for these new settings involving quantum field theories. Okay, so there are many interesting things ahead, but thank you very much for your attention.
Okay, thanks for the very nice talk. And is there any question?
Could you explain what is the reason for the name Resurgence?
Oh, Resurgence. Yeah, the name is because it's because when you look at this equation, you can see that the structure, the non-perturbative sector resurges in the perturbative one. So through the large order behavior, you can read the non-perturbative sectors by looking at these large order asymptotics.
Another question. You mentioned that you have to normalize
Yes.
functions, I think, phi.
Yeah, absolutely.
Is it easy to explain what is the...
Well, in complex Chern-Simons is very easy because they come from a saddle point expansion of a finite dimensional integral. And then, when you do this, there is a natural normalization. And then with this normalization, you have these integers. Now, for topological string theory, because you can say that, if you can change the normalization, what does it mean to have integers? What you do is you fix the normalization once and for all, okay? And there is a universal formula for all the phi omegas that appear in topological string theory. You can write down. And once you have chosen this normalization once and for all, which applies to all singularities, then you see that the Stokes constants are integers. Okay? So you have to be honest in the sense that you have to have a normalization. You cannot change the normalization for each singularity so that you get always an integer, right? You have to be consistent. But this can be done in both cases, in natural ways. Yes.
I have a very naive question. So on the Donaldson-Thomas side, you have the charge and the stability that goes into the definition of the T invariants. And so what do they correspond to in terms of the Stokes data when you consider them?
Well, the stability, okay, so you're talking about the Donaldson-Thomas invariance, right? And
yeah, so you have the Chern, in order to define Donaldson, the T invariant, you need the Chern character and the stability, right?
Yes, yes. Well, we know that when there is no, here essentially none of these things appear explicitly because you have an analytic theory for this invariance, right? So everything has to appear from the structure of the Fourier plane. Now, what we know is that when the stability conditions change, so there is wall crossing, this has to be reflected in the structure of the singularity, so they have to change this continuously. So this is how stability gets reflected in the Fourier plane. But there is no intrinsic notion of stability because we are approaching this in a completely different way. We are approaching this in terms of this analytic. So we don't really have a notion of stability here. The stability we get is for free in the sense that once a state is no longer stable, it will disappear from the Fourier plane.
But at some point you had on the slides you had the quality Stokes. Your Stokes factor is equal to some
yes,
invariant.
Yes. So, but this is yes. So here I have this equation. Yes. So this means that for a given choice of
what is CI and what is DI?
The psi is this is the Donaldson-Thomas associated to the D brane with these charges. So this is labeling charges. Now, there is some, I think there is maybe some issue here which might be worrying you, is that sometimes the space of stability conditions for Calabi-Yau categories is very big. It's like a double dimension than from from what I'm doing here, right? But on the other hand, we know in many cases in physics that you don't need such a big space of stability conditions. For example, in say Cyber-Witten theory, you know that the only space of stability conditions is the U-plane. So it's really complex one-dimensional. So this definition assumes that the stability only depends on the complexified Keller model. It doesn't depend on additional model. This is maybe something that I should emphasize here. Yeah. Yeah, no, I mean, you can use mirror symmetry. So I use a model for convenience, but everything here can be translated into the V model. It's just that these things now are going to be related to a symplectic basis in 3 homology, but everything, through mirror symmetry, I can make the statement for the V model. It's totally exchangeable. It's just that I want to stick to one description, and here I use the V model description. I could have used the V model description.
Thanks for the talk. So, Tommy Joyce has formulated wall crossing formulas for Donaldson-Thomas invariance in terms of mysterious vertex algebra structure on the modulus.
Yes.
On the modular space of modular space of cycles of modular space.
Yes.
And does this has an interpretation in terms of resurgence or?
I'm not sure about this particular thing. What I can tell you is that, for example, the formula, and this was on the basis of this thing, is that one of the reasons why we think this relation is correct is because in resurgence you can calculate what is called the Stokes automorphism, which is the discontinuity as you go through one of these ray of VPS singularities. And the formula you obtain is exactly the same formula that people obtain in Donaldson-Thomas theory. In particular, this very beautiful work by Alexandrov and Priorin, and you get on the nose the same formula. And when you compare the two formula, you see that this has to be true for the two formula to be equal. And this is really a calculation in topological string theory, which actually uses the holomorphic anomaly equations. From the holomorphic anomaly equations, you can compute the Stokes automorphism, and then you compare to Donaldson-Thomas theory, you find the same formula, and then these two things have to be equal. And this was one of the main reasons why we think that this relation has to be true, because it cannot be a coincidence that you get the same structure up to this equality, right?
I was wondering if you had an example in the topological string context where the saddle point approximation is not good enough in context. I'm primarily interested in examples where you can translate it to black holes.
Yes.
Where the semi-classical path integral that we've evaluated over the last many years has always been a saddle point approximation. And if there were contributions to the entropy or index that came from non-saddles,
yes,
that would be interesting. Wondering if you have any.
Yes. No, actually, I don't have any example, but I always tell people that even people doing calculating using these wormhole saddle points and so on. I had a discussion with Joe Pennington recently in Twitter about this, and I said, I think even in QCD, we know in the ultraviolet, in the infrared, all kinds of things can happen. But when I say that Renormalons give the leading correction to the perturbative series, this is in the ultraviolet. You're really working at large momentum. And still you see a correction which is not coming from a saddle point. But this is happening in QCD, in the gravitational path integral, I would expect all kinds of crazy things. Just that maybe we don't know enough, right? But I wouldn't be so sure. Of course, there are many successes of using gravitational path integrals. But I think one has to have an open mind that there might be things which are really unsuspected. I don't know what is the physics of this. In asymptotically free theories, there is this physics of condensation of operators and the OPE. So I don't know what would be an analog in the gravitational physics. Yes. I could think that there is some sort of this sort of operator condensation analog of this in gravitational theory, which actually would give you corrections to the perturbative series which are not saddle points. This has to be kept in mind.
Okay. Is there any other questions?
May I ask, since this resurgence seems not to depends on the supersymmetry, so
how many progresses we have made in understanding the non-perturbative nature of 4D Yang-Mills.
Well, in non-supersymmetric for the Yang-Mills, essentially the physics that you get from Resurgence is essentially this Renormalon physics that I explained. This is not something new. This is something that people have understood long ago, in the sense that, people understood long ago that Parisi and Toft already, that there will be these corrections and so on. Now, making these explicit calculations in QCD is very hard. So, but, people have, for example, there have been lattice calculations you can calculate, there is something that is called lattice perturbation theory, in which you can calculate long perturbative series, and people have seen that this gluon vacuum condensation, it's really controlling the large order behavior of perturbative series in QCD. So you can check this on the lattice. So we know that the QCD series knows about these non-perturbative effects due to gluon to this gluon condensation. So this is essentially what the Resurgence tells you about this. It's not a full description, and I have to say that I don't want to oversell Resurgence in actual QCD, because we know that many interesting quantities in QCD do not have a perturbative series. For example, take the mass gap. The mass gap of QCD, you can do the only way you can get a perturbative series for the mass gap is by using large chain. Okay, but this is a different story. You do but the mass gap doesn't have a perturbative expansion. So the Resurgence in QCD or in Yang-Mills is only good if you are already in a regime in which you can do perturbation theory. So you are in large energies and you actually calculate corrections to the perturbative series, but it cannot tell you anything about the mass gap in principle.
I see. Thank you.
Okay, we have a few minutes, so maybe you can continue to ask in the break, and let's thank the speaker again.